All right, so on this one, take down a couple little notes because it's going to talk about the Heisenberg's uncertainty principle again and the particle wave duality. A couple of things that we've actually talked about, but not in great detail. Okay.
You probably know that all stuff is made up of atoms, and that an atom is a really, 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 really tiny particle. Every atom has a core, which is made up of at least one positively charged particle called a proton, and in most cases, some number of neutral particles called neutrons. That core is surrounded by negatively charged particles called electrons. The identity of an atom is determined only by the number of protons in its nucleus. Hydrogen is hydrogen because it has just one proton. Carbon is carbon because it has 6. Gold is gold because it has 79, and so on. Indulge me in a momentary tangent. How do we know about atomic structure? We can't see protons, neutrons, or electrons. So we do a bunch of experiments and develop a model for what we think is there. Then we do some more experiments and see if they agree with the model. If they do, great. If they don't, it might be time for a new model. We've had lots of very different models for atoms since Democritus in 400 BC, and there will almost certainly be many more to come. Okay, tangent over. The cores of atoms tend to stick together, but electrons are free to move. And this is why chemists love electrons. If we could marry them, we probably would. But electrons are weird. They appear to behave either as particles, like little baseballs, or as waves, like water waves, depending on the experiment that we perform. One of the weirdest things about electrons is that we can't exactly say where they are. It's not that we don't have the equipment, it's that this uncertainty is part of our model of the electron. So we can't pinpoint them. Fine. But we can say there's a certain probability of finding an electron in a given space around the nucleus. And that means that we can ask the following question. If we drew a shape around the nucleus such that we would be 95% sure of finding a given electron within that shape, what would it look like? Here are a few of these shapes. Chemists call them orbitals, and what each one looks like depends on, among other things, how much energy it has. The more energy an orbital has, the farther most of its density is from the nucleus. By the way, why did we pick 95% and not 100%? Well, that's another quirk of our model of the electron. Past a certain distance from the nucleus, the probability of finding an electron starts to decrease, more or less exponentially, which means that while it will approach zero, it'll never actually hit zero. So in every atom, there is some small, but non-zero, probability that for a very, very short period of time, one of its electrons is at the other end of the known universe. But mostly electrons stay close to their nucleus, as clouds of negative charge density that shift and move with time. How electrons from one atom interact with electrons from another determines almost everything. Atoms can give up their electrons, surrendering them to other atoms, or they can share electrons.
That's called flip. When you donate an electron, and then you come together. That one, no. This one is the sharing. Co means together. That means to share. So that's a covalent bond. So that's a ionic bond. You can see the charges and everything. Like lithium fluoride is going to be coming together, and this is just hydrogen gas. So that's why this is so important, because in our next unit we're going over chemical reactions and bonding and nomenclature. So it does matter about where the electrons are and what do they do.
And the dynamics of this social network are what make chemistry interesting. From plain old rocks to the beautiful complexity of life, the nature of everything we see, hear, smell, taste, touch, and even feel is determined at the atomic level.
Okay. So that was pretty good on the where the electrons are and where they exist kind of thing. Can you think of an element that has no neutrons in its nucleus? What? No neutrons in its nucleus. Why B? Because the atomic mass of hydrogen is 1, and what's in it? 1 proton. That makes it the whole thing. Good. Oh, we have to. Well, we're not going to log in. We're just going to pretend we are right. Okay. Second question. Which of the following? Oh no, that's not what I want to do. The identity of an atom is determined by its number number of protons in its nucleus, right? Not number of protons and neutrons, it's just the number of protons in the nucleus. Electrons behave as particles or waves depending on how they are observed, right? Sometimes you actually can, like if, for example, if you shine light on something or if you excite an electron with fire and then you observe it, you can't observe the electron necessarily, you can only observe how it changes. You can observe as it jumps from an excited level down to a lower level, and you observe it as a wave, as a light wave. But we know it's the electron doing that nonsense, right? It's not just like, ooh, random colors, cool, right? It's all about how the electron's behaving. And then, okay, we're done with that one. I just want to go through a couple of those. All right, any questions on electron configurations or orbital diagrams right now? Let me do one example. Yeah, let's do nitrogen. I want to do the electron configuration and the orbital diagram of nitrogen. Okay, nitrogen. I'm going to try to stick with a short one right now. Okay, so for nitrogen, it's the electron configuration across the rows or doing your diagonal method, whatever works for you. Tell me what that is right now. 1s2. So when you're still in the second row, you're still in 2, but you're in P what? P3. What is that's the long form, right? What's the short form of this? What's the noble gas shortcut of this? Bracket. So you're going back to the last noble gas, which happened to be helium. It's just a small atom. Okay? 2s2, 2p3, because that 2s2 starts the next row. So that one's really tiny, right? Now, if a nitrogen formed an ion, what ion charge would it form? What charge? Be confident. Say something for me. -3. Who said -3? Good job. Why? It wants to look like the noble gas electron configuration of neon. So instead of stopping at 1s2, 2s2, 2p3, you allow nitrogen to gain 3 electrons to look like neon, so it's 2p6. So what's the electron configuration shorthand? Bracket neon. So that's how you know you're right. The electron configuration should be that of a noble gas, because that's the only reason you would ever lose or gain electrons. It's not just for kicks and giggles, it's for a purpose. Yeah.
I read somewhere that you're supposed to put the atomic number under the initial cut. Do you want to see that?
No. I gotcha. I understand what you're doing. Yeah.
If you start on the F clock, you start on the energy level you start at 4, right? So it'll be like
yes. So it'll be 6s2, 4f, 6s2, 4f, whatever. Yeah. I'm going to ask you to do both. So let's do an orbital diagram though, just to be sure we know what the orbital diagram is. What's the difference between electron configuration and orbital diagram? What do those look like?
the lines with the up and
Right.
down.
So it's like literally a diagram, right? It's like a picture. So what is the electron configuration? I mean the orbital diagram of nitrogen. What do I write? 1s. Up and down arrow. That's 2 electrons. So next is 2s. Up and down arrow. Why are we drawing 3? Because the p's come in 3s. Okay. How do I draw 3 electrons? Up, up, up. Because whose rule is that? Hund's rule. You do one at a time, and if you have to go back and polypair them up, you polypair them up. Okay? All right, let's do this. Clear up your desk. All you need is that periodic table and a pencil in front of you. The blue periodic table is not your sheet. Yeah. 1, 2. Yes. Yes. Yeah. How many electrons are there? How many electrons across there? You tell me right now. So how many orbitals do you need for all 14? Okay, I'm going to pass these out. You should write on this piece of paper, put your name on it someplace, and then on the back, I'll ask you to draw the orbital diagram because there's not enough space there. So if you're sitting next to somebody, just keep your eyes on your own quiz, or you won't have any eyes. This should take us no more than 5 minutes. Seriously, people, 4 questions. You were smart. If you did problems at 5 as a trustworthy person, you should know what you're talking about. And you know what? I'll let you choose. One of those four you need to draw an orbital diagram for. Your choice. On the back, please. Alright, pass up this quiz right now to me. Okay. Tasting and timing the essence of the essence of me right here. So, of those, that's all from here. Okay. Oh, come on. Pass them up. Pass them up. Okay. Of the four, what was the most challenging of them? The last one? Okay. The 10-4? 10-4 plus? What do we do? What do we do with it to make it a 4 plus charge?
Take out 4 electrons.
Which 4 electrons? They're not just any. That's craziness, right?
The valence ones.
Which ones?
The valence ones.
How do you know which one the valence ones were?
They were on the 5th energy level.
There you go. 5th energy level is the very outside energy level is the 5th energy level. So you would have dropped off a 5s2 and a 5p2.
But what does that? Does it drop back to silver?
It has the electron configuration of whatever this goes to. Krypton. It looks like silver because it's only got 47 electrons, but it's the way the configuration is. It's because that you have a full fourth energy level. That means your full fourth energy level goes to krypton. So that's why it looks like noble gases, because it's the full fourth energy level. So that was the hardest one, I think. Me too. Okay, so let's look at a graphic organizer, and you guys are going to shout out things like, I made a huge graphic organizer of things that I thought related to this unit. Mine is a little crazy, right? So I want you to do that with you guys. And I started this off. I think that you guys will start to see the point and see how these things are connected. I start you off at the middle of the periodic table, and then how the atom is related to that, and we're going to talk about everything about the atom, and then periodicity being periodic terms. So I'm going to use my cheat sheet, but I want you to see what you guys can give me, okay? So you can just sketch this as you go. This is a really good study tool because it can kind of show you the connections off between everything. So if I start you off with the atom, let me just say the atom. What are things you think of when you hear the atom? Things we've talked about. Concepts. Shout them out.
Protons, neutrons.
Okay, so structure. I'm hearing structure and of structure. I can write this a little bit neater here for you. Of structure, I'm hearing protons, electrons, and neutrons. Okay? What else do you think of when you hear the atom? The atomic mass, that relates to maybe more along the lines of isotopes, right? So of the atom, you can also have isotopes of the atom, and they have what? They have they have an atomic mass that's different based off the number of neutrons, right? Okay, do you guys think of anything else? Maybe related to electrons? What can we do with electrons now?
Ions.
Oh gosh, we got ions. I totally forgot about ions. Ions are here. So of the atom, you can have ions. There are 2 types of ions.
Cation and anion.
Cations and anions. Okay. Okay. So give me more. I think the electron is very, very, very important. So I'm actually gonna make it a little kind of category. Okay. Of the electron, what can we do now? We know so much about electrons. How do we know where they are? What do we write about them? Electron configurations. Okay, so from the electrons, you can write electron configurations. And where do the electron configurations, where does it say the electrons exist in? What kind of orbitals? I'm just going to put orbs. And they come in how many varieties? S, P, D, F, right? All right, so that's cool. They have shapes and stuff. Who made up this random SPDF stuff? What is it all related to? What model of the atom is it related to? What's the modern model called? Okay, I'm going to go like this and say quantum. Okay, so that's all related to the quantum mechanical model of the atom. The quantum mechanical model talks about electrons and their activities and what they can do. What was our lab based on yesterday? Exciting and then allowing them to drop back to ground state, right? So the quantum model and Bohr actually kind of both say electrons can move, but how do we see them move? We can't see them move, we can see them fall. And so the quantum model, I'm going to put quantum and Bohr, just so I have some extra details we can add here. They relate to the electromagnetic spectrum, or the electromagnetic spectrum, electronic energy levels and all that jazz. And then, let's see here, I was going someplace with this. Going someplace with it. Particle wave duality. No, I'm just gonna put Bohr model. Okay. The EMS, the electromagnetic spectrum, relates to what? What are some things we know about the electromagnetic spectrum? Maybe even formulas. What are some formulas or some other things we know about the electromagnetic spectrum? I hear C. Okay, so that's the speed of light, which is a constant equal to wavelength times frequency. Planck's constant, H times V again, so frequency. Okay, and we know that we've got, I'm going to kind of just put light as a separate category here. So these are equations that go with the electromagnetic spectrum. Light is a separate category because it relates to electron, I'm going to say emission spectrum. Of the atom. So remember, each atom has a specific set of wavelengths that it can emit due to its electronic transitions. And so that's all related to our relationship with light, that we can see light, so we can see that kind of electronic motion and movement. And just as an aside, how do we excite these electrons? There's a couple ways. Okay, so you can shine really high energy light on them. You can heat them up with fire, or say again? Electrocute them, so add electricity to them. Okay? Back to Bohr model. So actually, you know what? I think this relates to the Bohr model entirely. So I'm just connecting Bohr, because Bohr really we mentioned a lot about that, and basically the Bohr model is the one that has the energy levels where they move up and then they fall back down, which is related to all of that anyhow. What's up? I just said how do we excite electrons? Light, we can shine really high energy light on them, we can heat them up, or we can we can shock them and they excite and then fall back down. And the falling back down is related to Bohr's model. Okay, so that's a lot of the atom. We got ions. Okay. Oh, and we mentioned some scientists, though. I think we could really mention some other models, right? We could mention whose model? I don't know where to connect this. Okay, so I'm going to say models. Okay, and you're going to say, who's the very first person to describe the model of the atom? Okay, I heard Dalton. I'll go with Dalton. Keep going. Who's next? J.J. Thomson. Okay. Rutherford. Well, hold on. Who's after J.J.? It starts with an M. Oil drop experiment, right? So Millikan. Then Rutherford. Then Chadwick. And then Schrodinger, or Bohr and Schrodinger, right? So we've learned a lot about them too, but we were pretty much pros on their models, I think, because we were those people on Monday, so we should know. Okay, so that's a lot about a lot of stuff regarding the atom and the electron. I'm going to draw, you guys' charts are like great. My board is only so big, so I can only write so far. But I'm going to draw myself a line. Got me another connection here. Let's talk about periodicity and periodic trends. So let's go ahead and start off by just listing the periodic trends. So periodicity. What are the 4 periodic trends? Yeah. AR, atomic radius. Electro what? Negativity. Affinity, right? It's love for electrons. Okay. IE. Ionization energy, right. Okay, and periodicity is just a trend of the periodic table, right? We know that the atomic radius plays a role on the rest of these, right? So let's make kind of a general statement about all of these and their direct or indirect relationships. So smaller atoms have what in reference to like the scale or the size of each of these energies? Do smaller atoms have a high ionization energy or a low ionization energy? Huh? High or low? Strong, high energy have, I'm going to say, a large ionization energy, and EA and EN, because they're all run the same direction, periodic table. And how do you remember that? Right, there you go. Picture the periodic table. You guys are like, right hand what? Right hand radius. Okay, so if you don't remember it, it's like this. Right hand radius goes that way, increases as you go to the left on the periodic table and down, and then everything else increases this way, i.e. EA, EN. Now, there are two factors we talked about yesterday that are explanations that explain why something has a smaller radius or why something has a high IE. Two factors. Go for it. Okay, so the shielding effect, and that relates to energy levels. I'm going to say number of energy levels, because it's all about the onion, the layer by layer by layer. Doesn't really have a whole lot to do with protons, right? So tell me more. What is that ZEFF? Z-E-F-F. Nuclear effective charge. Nuclear effective charge. I kind of abbreviated it. And that is going to tell us more about the strength of the nucleus. So we're comparing apples to apples here. We're comparing the protons of one nucleus to the protons of another nucleus. Okay, let me make sure. Can you guys think of anything else that kind of goes into this? Oh, I just thought of something. You guys got anything else?
Energy levels.
Energy levels, we got it here, and I think we've got it kind of taken care of here with like the Bohr model and more. What else have we talked about? Took notes on them without me. So we got kind of the trends, but more along the lines of the properties in the groups, maybe, right? So you guys took notes before trends on properties, right? So the periodic table, where's that periodic table? PTOE. I'm going to put another line in red over here. I wish I could move sideways. Okay, here we go. Moving sideways. Nope. Yes. Okay. I don't have an extra page, so it's useless. Okay. So you told me trends. You told me continuation. I'm going to say properties. Okay, so properties of metals and nonmetals. Give me a couple. Give me a couple. Yeah, shout them out. Luster. Okay, shiny. What else? Malleable. What else? Conductive in their solid states. Give me nonmetals. Gases. More. Not malleable, not conductive. Right? So not conductive and so forth. You guys have a lot of those properties in your paper, but that's another subcategory of our unit, this unit. Our properties of matter and metals and nonmetals specifically. I think also kind of leading into properties, the real reason these properties differ is because they're valence electrons. Their valence electrons control those properties. So valence electrons, group 1 down to group 8, have how many valence electrons in group 1? Group 1A. 1 valence electron, 1 electron. How many in group 8? 8 valence electrons, and everything in between just follows the rule, right? So a lot of those valence electrons kind of play into those properties. I think I'm I'm gonna go back to electron configurations and add some names here. Oh, you have some space? Me too. Someplace. Here we go. Electron configurations. Give me the names that relate. I heard off-ball, Pauli exclusion principles, and Hans-One's rule, okay? So, gosh, look at this, guys. We've really talked about quite a lot, and you've got to find a better way for yourself to organize it, because it does start to kind of condense together, and you're like, oh, do I have to include units here? Yes. Do I have to share my math here? Yes. Do I have to know this person's name? Most likely. Okay, so make sure you go back and you remember that stuff. You look through your stuff to help you figure out where you're still fuzzy. Okay, because our test is Wednesday. Monday we are doing nuclear decay. Tuesday we are doing review day and presenting our carbon fibers. And Wednesday is our test. Okay? Okay, the rest of the time is yours for carbon fiber research. If you do not remember where stuff is on my website, it is under Thursday night. I might be lying to you. From last week, or am I at Monday? Okay, there it is. Thursday from last week and Friday from last week have 2 links. And you can see the rubric. If you go here, it's got all the information. I actually added some highlighted things under the projects, the crafty part of it, where you might need to find some extra information. Or like, you should video this before Monday or Tuesday. You can use a screencast-o-matic thing. So make sure you're assigning roles and making sure people are getting stuff done today. The computers are for you. You have a little under an hour. Okay? Go.